Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So any questions from last class? Can I ask questions from last class? Nothing, everything was super clear. Okay, so I got one question by email, so let me share that question with you. So you remember in last class we studied Bernoulli distribution, that is, let's say x is from Bernoulli distribution with mu if probability of x being 1 is equal to mu, right? And then I said that maximum likelihood, so suppose I observe some trials of this Bernoulli distribution, that is I take my coin, toss it 10 times, and then I want to estimate the underlying parameter mu, that is the probability of heads. I want to estimate that, and I said that my mu ml is equal to summation xi, I goes from 1 to n by n. Okay, and then I made a very vague statement that if n is small, then this estimate is not good. This can be very bad. So the question was that is there any formal number or formal threshold that okay, if you take these many samples, if your n is let's say 1000, then I will not see more than this much of error. Does anyone of you know the answer to that question? So essentially what I want to say is that I want to estimate how far my mu hat ml will be from true mu. And naturally this is a probabilistic process, so I want to estimate, I want to say that with probability 1 minus delta, this distance is bounded by something. Okay. So actually this is a somebody said something? Okay. No, but now you have to say something. Yeah, precisely. So there is a very popular line of like research called concentration bounds. It was sort of initiated by I think Chernoff, and to bound this we can use something called Chernoff-Herding bound. So one comment I got was my board work is amazingly bad and I need to write bigger. So I'll try that. Chernoff-Herding bound. So what it essentially says is that if you have let's say some random variables x1, x2 till xn, all of them are independent of each other. So here also all our trials are independent. Okay. And we don't assume anything else. We assume that they are independent. Then 1 by n summation xi minus 1 by n expectation of xi summation or all I. So the probability that this thing is greater than equal to some epsilon is less than equal to e to power minus epsilon square summation epsilon square n square summation bi minus ei square. So we assume that each xi is bounded by bi and ai almost surely. That is with probability 1, each of my random variable xi is bounded between bi and ai, and then the chances that the average of these xi's is too far away from its mean is small. So when we apply it to our problem, we know that so we have 1 by n summation xi, which is essentially mu hat ml, and then expectation of each xi is equal to mu, because each one of them is a Bernoulli random variable. So this will be mu. So probability that this is greater than equal to epsilon is less than equal to e to power minus epsilon square n, because this bi is 1 and ai is 0. So this will come out to be n. 1 n cancels. I think there is a factor of 2 here and 2 here. So, but that's not very important. So what this implies is that, so this is my error probability, right? I don't want this difference to be greater than error, that's epsilon, with some probability, right? So suppose I bound this probability by delta. I set this probability to be delta. Okay. So I know that with probability 1 minus delta, mu hat minus mu will always be less than equal to epsilon. Probability 1 minus delta, this thing will be less than equal to epsilon. And now I'll just figure out the epsilon. So this, when I set this to be delta, my epsilon will come out to be something like root of log 2 or delta by 2n. Okay. So what this says is that with probability 1 minus delta, distance between like my true mu and the mu that I estimated will be of the order 1 by root n. Okay. So suppose I want at most an error of 0.01 in my estimation, then essentially I'll need around 5,000 trials. Okay. I need to do 5,000 trials of my coin, and I'll guarantee that I'm around 0.01 distance away from my true mean. Okay, is that clear? All right, so this is from last class. Let's move on to new topic. The board is so today we'll sort of do a refresher course on linear algebra. Okay. So one of the most like fundamental quantities in linear algebra is vectors, and in today's class and actually throughout the course we'll always assume that we are dealing with only real numbers. Our vectors are in real space. That is, so suppose if I have a vector x in d dimensions, then I can write it to be, x belongs to r to power d. And what this essentially means is that x is x1, x2 till, okay, each one of them, each xi. So xi is the ith element of this vector x, and it is a real number. Okay, and since it's a vector, so basically a vector has two things. One is direction, and one is like also magnitude. Right. Again, I started writing very slowly, very small, but okay. So magnitude of a vector can be measured by something called norm, and you can define norms in several ways, but every norm should satisfy three properties. So so if x is a norm, okay, then number one, it should be non-negative. Okay, it should be greater than or equal to 0, and it should be 0 if and only if x is 0, that every single entry in x is 0. Okay. Second property is homogeneity property. For all scalars alpha x, norm of alpha x is equal to norm of x multiplied by alpha. Okay, and then the third property is triangle inequality. Okay, norm of x plus y is less than norm of x plus norm of y, and there are several norms which well-known norms. So first is your L2 norm, which is summation over I is equal to 1 to d xi square. And similarly, you can define, let's say, L1 norm, which is L infinity norm max over all I. And then in general, LP norms. So your vector LP norms are okay. So this is basic linear algebra. So now let me define inner product. So okay. So norms also sort of give rise to inner product. So one of the most popular inner product is your extended inner product, which is xi yi. Okay. And this can also be thought as cos theta, where theta is the angle between vector x and y. That is, so let's say we have vector in 2-dimension space. So let's say this is one vector x, this is another vector y, and this is the angle between x and y. Okay. So the inner product between x and y will be given by norm of x multiplied by norm of y multiplied by cos theta. The theta is the angle between the two vectors. Okay. And so this says that my cos theta is equal to inner product of x y divided by norm of x norm of y. And so this represents in some sense similarity. That is, let's say if theta is 180 degree, that is something like this, then naturally the two vectors are not similar at all. And that's what will happen. Cos theta will come out to be -1. Okay. So this is also called cosine similarity. And it's heavily used in text data and to compare data whose norms is almost similar. Okay. And then similarly, we can use norms to define distances. So our popular Euclidean distance or L2 distance is norm of x minus y 2 norm. And similarly, you can have, like with every, you can have Manhattan distance or L1 distance as x minus y 1 norm. Okay. Okay. So now what? Okay. So let me define now vector subspaces. So a vector subspace is a set of vectors which is closed under vector addition and scalar multiplication. Okay. That is S is a linear subspace if x belongs to y, sorry, S, y belongs to S implies x plus y belongs to S, and okay. And then let's also define linear independence of vectors. So a set of vectors x1, x2 till xn are independent, linearly independent if a linear combination of them equal to 0 means that coefficient of each of the vectors is 0. In other words, we cannot express one of the vector in terms of other vectors. Okay. And then Okay, so and then basically we can define basis of a subspace. So basis of a subspace S will be maximal set of vectors which are linearly independent. Okay. So if let's say x1, x2 till xn are all linearly independent, they all belongs to S, and if I add one more element to this set, then they will become linearly dependent. That is their maximal set of independent vectors. Then this is called a basis. Okay. And since by adding one more vector they will become linearly independent, that means that I can express every single vector in my subspace in terms of just these vectors, these n vectors. And now n is called dimensionality of the subspace. Okay. So one simple example is, let's say in 3 dimensions, you take a plane that passes through origin, and now that is a 2-dimensional subspace because you can find only 2 vectors that will be linearly independent. As soon as you add third vector, you can represent that third vector in terms of the other 2 vectors. And then there is something called orthogonal basis. So if each of these x1 to xn are orthogonal to each other, so let me define orthogonality. So x and y are orthogonal if their inner product is equal to 0. Okay, that is, so in 2 dimensions what this means is that their angle in every dimension, actually the angle between them is 90 degree, because we know that x inner product y is norm of x norm of y times cos theta. Norm of x and norm of y are not 0, they are non-zero vectors. So that implies that cos theta should be equal to 0, that theta is 90. So basically if 2 vectors are at 90 degree, they are orthogonal. So a orthogonal basis is where each of the underlying vectors are orthogonal to each other. Okay. And you might have read that if you have, like you give me any basis and I can convert it into an orthogonal basis by using something called Gram-Schmidt orthogonalization process. That we will not go into. Okay, so now we have defined basis. So now we can easily move on to matrices. So this is just very brief refresher for vectors and subspaces. So consider a matrix X in R to power, let's say m by n. That is, it has m rows and n columns. Okay, and I'll always will always represent xij as ijth entry, that is ith row, jth column, and xij is the ijth entry of matrix X, and then x transpose is the transpose of this matrix, that is take each column and convert it into a row. So x transpose will be in R to power n by m. Okay. So similar to vectors, we can define norms over matrices as well. Okay. So one of the most popular norm is Frobenius norm. Which is essentially, so Frobenius norm of X is equal to so it is essentially 2 norm of this matrix X when we just just make it a vector. That is, take each column of this matrix and just stack them one after another. So it will be a big vector of dimensionality m by n, mn, and this Frobenius norm is just 2 norm of that long vector. Okay. And then another interesting norm is, or a very popular norm is spectral norm, and that is defined by max over all y xy2 divided by, so this is called spectral norm or 2 norm of this matrix. Okay. And this is in fact a special case of a general family called vector induced norms. Although this will be most useful, I mean Frobenius norm and spectral norm will be most useful for this course, but I'll just define general vector induced P norms. Okay. So now one quick question. Can you tell me? Yeah. Go ahead.
What is y plus?
Y is any vector in R to power n, if x is in R to power n by n. Y is any vector, yeah. So x times y is a matrix vector multiplication. So, okay, let me define that as well. So let's say x is a matrix, y is a vector. Okay, then I can write this as in two ways. So xi inner product with y, so x1 inner product with y, so on till xm inner product with y, where xi is ith row of matrix X. Okay, so it's a vector. I'm taking inner product of this vector with y. Okay, and another way to write it is, which I find very useful, is yi xi, where xi is the column of x. Okay. Okay, so where were we? P norm, vector induced P norm of x is given by this P norm of xy divided by P norm of y. Now one question I have is, what is one norm of, vector induced one norm of matrix X? Can anyone tell me? Huh? Max eigenvalue. First of all, X is a m by n matrix, so it need not have, like it's not a square matrix. It's a fat. It can be a rectangular matrix, so even eigenvalue might not even be defined. And eigenvalue or singular value connection is to 2 norm. This is very much easier. Precisely. So this is given by max over all I summation or all j summation xij. So 1 2 n. So take a column, add all its entries, absolute value of its entries, and select the one which has the maximum value, and that will be your this one norm. Okay. And how this follows, I think this should be an exercise. Derive how L1 norm of x. So I'm pretty sure nobody will do it, but still let me no exercise. Oh. So derive this and similarly infinity norm of matrix X, vector induced infinity norm. Okay. All right, so let's move on. Okay, so there are some interesting matrices, like one is diagonal matrix. So diagonal matrix is a square matrix. A square matrix is where m is equal to n. That is, x belongs to R to power n by n, and only non-zero entries are on the diagonal. Okay. And then there is a symmetric matrix where xij is equal to xji. Symmetric matrix is also a square matrix. Then there are something like anti-symmetric and all, but I'm pretty sure those are not that interesting. Then orthogonal matrices. So orthogonal matrices has this property that every column of this matrix is orthogonal or perpendicular to every other column. That is, xi inner product with xj is equal to 0, where xi is the ith column of matrix X. Okay, and then orthonormal matrices are when you have an additional thing, that is xi 2 norm is equal to 1. That is, if X is orthonormal, that means that X transpose X is equal to identity. Okay. And what would be the size of this identity? N by n. Okay. So now we'll study one of the most interesting decompositions of in linear algebra, singular value decomposition. Okay, so suppose you have a matrix X in R to power m by n. Let me represent it like this. So it's a thin matrix. So you can write this matrix as multiplication of 3 terms: U, sigma, and then V transpose. Okay, so U will be m by n, sigma will be n by n, V transpose will also be n by n, where U is a orthogonal matrix, that is U transpose U is identity. Sigma is a diagonal matrix, that is only diagonal entries of sigma are non-zero, and V is again an orthogonal matrix, that is V transpose V is equal to V transpose is equal to identity. Okay. And nice thing about singular value decomposition is that you can do for every single matrix. Every matrix you can decompose as a product of 3 terms, U, sigma, V transpose, where U and V are orthonormal matrices and sigma is a diagonal matrix. Yeah, here I am assuming m is greater than n. As I said, that I am assuming a thin matrix. You can do the same thing if you have fat matrix. I'm sorry?
Yeah, if it's a thin matrix, you just take transpose
and then do the same thing. Okay. So this decomposition is interesting at several levels. So first of all, it is very heavily used in several applications, like your principal component analysis essentially just does SVD, and it also gives a sort of very nice intuition for this matrix X, or like your matrices. So using this decomposition, you can think of the matrices as just operators. So that is, suppose I have a vector y in R to power n. Okay, let's say I have a vector like this. This is my y vector. So when I apply x, it will give me some vector xy, right? So this sort of clarifies that how exactly this matrix X manipulates this vector y. So essentially, since I know that x times y is equal to U sigma V transpose times y. So what this says is that when I multiply y with x, first it is multiplied by V transpose, and V is a orthonormal matrix. That is, it will only, so it's a sort of rotation matrix. It will only rotate my vector. It will never change its length. So it will take this vector as it is, and it will rotate it in some direction. Okay. And then there is a operation sigma, which will scale my vector in different directions. It will only scale my vector in different directions, so I can get another vector which might be smaller, longer in certain directions. Let's say this is y that I get, and then I again apply U to it, and again U is an orthonormal matrix, so it will just rotate my vector. So it might rotate it to give me some vector like this. Okay. So the scaling business, entire scaling business is just handled by sigma. Okay. And furthermore, it has several other, like it captures several other interesting quantities. So for example, it captures range of my matrix X. Okay. So what is range of a matrix X? So X now, like you can think of as a operator, right? It takes these vectors. So what does X do? It takes these vectors in N and projects them or transforms them into vectors in M. It will take a vector Y, it will multiply X, Y will give me a vector in R to power M, right? So this is like, if I take entire this subspace R to power N, this will map it to some small subspace of this entire space R to power M, right? And range is what all vectors does it map to? That is, range of X is set of all vectors Z in R to power M such that X is equal to, Z is equal to XY and Y is in R to power N. Okay. And then there is one more interesting set, which is null space of X, which is all Y's in R to power N such that XY is equal to 0. Okay. That is all vectors Y which map, like whose image is 0 when applied X. Okay. So this SVD directly gives me range and null space of this space. So if you look at this matrix U, if you so your range of X is given by range of U, that is U is a basis for the range. Okay. That is, range of X is given by summation alpha I ui for all alpha i's. You can select any alpha I, and this vector will be in range space of my matrix X. Okay. And there is one more important property that so range of X is also called like dimension of range of X is also called rank of X. Okay. So rank of X will be the number of non-zero singular values. Okay. So I have singular values sigma 1, sigma 2 till sigma n. So sigma 1, sigma 2 till sigma r are, let's say, strictly greater than 0, and remaining all of them are zeros. Then in that case, I can say that the rank of my matrix is R. So if you are given a matrix and you are asked what is the rank of this matrix, rank is essentially dimension of your range space. Okay. So you are or in other words, how many columns of X are linearly independent. Okay. So what you can do is compute SVD, see how many singular values are non-zero, and that will be your rank. Okay. Yeah.
Given that the range is the column space of U, right?
Yeah.
But the columns of U are independent. That's what
So yeah, columns of U are independent.
then that means the dimension has to
So I have to write here I is equal to 1 to R. So basically what will happen is that you will have sigma 1, sigma 2 till sigma R, and remaining all of them are 0. So these columns, the first R columns will matter, all the other columns will have coefficient 0. Okay. So if you wanted to write it to be n, then what you have to do is multiply it by sigma I. So sigma is 0, that means that this column will not participate at all. Okay.
But the other columns of U should not be zeros.
They need not be 0, and they should not be 0.
Should not be zero.
It's just that they won't matter because coefficient corresponding to them is 0. Okay. So actually using SVD I can write this matrix X as I is equal to 1 to R sigma I ui vi transpose. Okay. You can write it in this way as well. Okay. All right. So there is one more good property that, remember we talked about a spectral norm of this matrix X. You can show that a spectral norm of X is equal to largest singular value of X. Okay. So maybe I didn't define it properly. So all the entries on this diagonal are called singular values. This is called left singular vectors. These are called right singular vectors. So your 2 norm of matrix X will be equal to largest singular value of X. And okay. All right, so let me state one more important property of SVD, which is why it is extremely applicable in several applications, especially in text and all. Like why is SVD used for PCA? So this theorem is precise reason. So what does this theorem say? That suppose, yeah, so let's say I have X in R to power m by n, okay, and let there be another matrix X hat or Xk, which is also m by n matrix, but Xk is a rank k matrix. Okay. Then X minus Xk will always be smaller, this Frobenius norm, and in fact 2 norm also, it will always be smaller than X minus UK sigma k Vk transpose, where UK is, so if, let me rewrite it again, so if this is my SVD, so UK will be taking just k columns, largest columns of my matrix X, like so left singular vectors of X, taking top k singular values, so let's say sigma 1, sigma 2 till sigma k, and then similarly take corresponding k columns of V transpose, sorry, rows of V transpose. Okay. So UK is just k columns of left singular values, of left singular vectors. Sigma k will be just k singular values, and then Vk will be again k rows of this matrix V transpose. Okay. That is, just select the topmost singular vectors corresponding to, like, basically the largest singular values. All right. And what you can say is that, I'm sorry, what you can say is that this rank K matrix that you have now constructed is the best rank K approximation to matrix X. You can construct any rank K matrix, okay, and the distance of that rank K matrix will be larger than this matrix constructed using SVD. Okay. So let's think about it. So what does it mean? So suppose you are given a set of points, okay, and all the points are so let's say we are in 2 dimensions, and we are given a set of points in 2 dimensions, right? Okay. And now what I want to do is, so these points are in 2 dimensions. I want to project them into 1 dimension to visualize them properly. Okay. So how do I, like, which direction I have to select to project to? So if I want to project them to 1 dimension, I can select any direction, right? This is 1 direction. So what I can do, projection means that I can just map these points onto this line and take the values. Another direction can be this. Another direction can be this. So which direction should I select so that my points are well preserved? That is, if 2 points were sort of nearby earlier, they should be nearby later also. My properties are not destroyed. Okay. So we can take one example, right? So suppose what do I take? Let's say, so earlier example, let's say these are our relevance and these are our click-through rates. Okay, and I just want to map this whole thing into one dimension, so that if my relevance and click-through rates are similar, the map points should also give me, like, the 1D points that I get should also be close by or should be similar. Okay. So that direction will be basically a direction that approximates these points the best, right? And it will be, since it's a one rank projection, so essentially the matrix that you get will be rank 1. So I have to find a rank 1 matrix that best approximates my set of points. So for that I will do a rank 1 SVD, and I will be guaranteed that that direction will be the best, the optimal direction. I cannot do any better than that. Okay. And that's what the main idea about principal component analysis also. These are, like, in principal component analysis, these directions will be called principal components, and those components are essentially the largest singular values of singular vectors of this matrix X. Okay. The direction will be given by U1, the largest singular vector of matrix X. And the way I form matrix X will be just stack all my points x1, x2 till xn. Okay. Is it clear? All right. So this is one very important application. So let's now just consider one more learning type of application. So let's say I have text documents. How many people have heard of TF-IDF? I'm sure almost all the IDC folks should have heard of it. So let me just still write it down. So suppose I have a set of documents or collection of documents, D1, D2 till maybe, let's say, DN. Okay. And each document can have, like, and I have a collection of terms also. Like, looking at all the documents, I have collected some small number of terms from them, like the maximal set of the terms. And let's say there are m such terms, or m words basically. Okay. Word 1, word 2 till word m. And then I form this term document matrix where ijth entry of this term document matrix is how many times word I occurs in document J. Okay. So this will give me this big matrix, and I can then, and basically each of these vectors can be thought of as a vector space representation of this document dj. I can represent each of these documents in this space, right? Okay, and then I can, since now I have these vectors, I can maybe, figure out if two vectors are similar or two documents are similar by looking at their Euclidean distance or some other distance, or I can figure out how similar they are using, let's say, by cosine similarity that we defined earlier. Okay. So, but one big problem with this approach is that there are certain terms which are not very useful, which are there in every single document, and that's why they will just skew my distribution or skew my vectors and make my vectors useless. So for example, term the or occurs in every document multiple times, right? And their distribution should not affect how I view these documents. So suppose I have a document about, let's say, linear algebra, I have a document about probability theory. I won't be able to say that, okay, they are two different documents, they are far away. But if these vectors are skewed heavily by how many times the is present and how many times a is present, it will be useless. Okay, those are not very important terms. So how do I get rid of, effect of such terms? So I can use basically what I can do is I can multiply this Tij by inverse document frequency of word I. So inverse document frequency of word I is log of total number of documents, which is n, divided by how many times, that is number of times term or word wi occurs in documents. Okay. So if some word occurs in every single document, it is useless for us. It is not, we won't be able to use it to make any like predictions on the basis of that. We won't be able to say that, okay, on the basis of distribution of this document is related to science or to maths or anything. Okay. And then there is one more term, Sj, which essentially all it does is it normalizes. So let me call this as now my Gij. So this Sj will ensure that summation Gij square, summation overall I is equal to 1 to m, that is this vector, the length of this vector is equal to 1, length in terms of L2 norm. Okay. So I am assuming that each document Dj can be represented by, let me get rid of this, by this vector Gj. Okay. And what I want is that the 2 norm of this vector Gj is equal to 1, so that all the vectors are normalized, and now when I compute, let's say, distance between them, the distances are normalized. Okay. So this is called TF-IDF representation of documents. Okay. And now, like there is one, so suppose I have a collection of documents. I give you one new document, and the goal is to recover the most similar document. Okay. The main challenge there is that if I just blindly use my cosine similarity, if let's say I have a case where two words mean exactly the same, that is, they are synonyms. Now what can happen is that one vector has, or one document has only one of the words, second document has only the second word. I will say that, okay, those two documents are far away because these two words like they don't have any common words. So there is this problem of synonymy. Similarly, there is a problem of polysemy, that one word can mean two different things in two different documents or two different contexts. And if I see that, okay, oh, this word is present, I will just try to say that, okay, these two documents are similar. So I don't want that effect. I want to get rid of that effect. So one of the most popular way to get rid of that effect is through SVD. And this approach is called latent semantic indexing or latent semantic analysis. So what you do is you form this matrix of TF-IDF vectors. You take its SVD and let's say project onto top 10 singular vectors or 100 singular vectors. That is, take 100 rank approximation of this matrix. And empirically people have shown that this will get rid of your synonymy and polysemy up to some extent. Okay, is that clear? So let's say this is your matrix A. What you do is you take its SVD, so A is U sigma V transpose, and you form a rank K matrix which is formed by UK sigma K VK transpose, and you use this for your retrieval. That is, now this AK matrix will also be a M by N matrix. Okay, given a new document, what you will do is you will use UK to project it into this K dimensional space. That is, suppose I give you a new document D, then what you do is you compute D hat by UK transpose D. Okay, and now use this D hat document to figure out which of your document from the database is most similar, and the similarity you can use your cosine similarity, let's say. So is that clear? And people have observed that empirically it gives good results. Let me just show some slides from my advisors.
I actually wanted to ask that could you give me an intuitive idea of why this thing works? That is
this latent semantic analysis that you told about, right? So I mean intuitively, why this works.
Okay, so one intuition is that if you have, let's say, some synonymous words, or so let's consider this problem of synonymy, right? So if the words are synonymous, then they will occur in very similar contexts. That is, the remaining vectors will be very similar, right? So let's say I have 10-dimensional vector, and 9 dimensions will be very similar, and this 1 dimension will be a bit different. Okay, in fact, sorry, 2 dimensions will be different, corresponding to these 2 words. And now what will happen is, speaking to a speaker, and now what will happen is that since the remaining things are similar, the latent semantic analysis will think that this one vector is sort of a perturbation of the other vector. Okay, so did you get it? That is, one document is just the another document with some noise, and the role of this SVD will be to remove this lower order noise. So let me maybe make this a little bit clear from board. So let's say I have this document and this document. Let's say document 1 and document 2. Both the documents are about, let's say, linear algebra, but there is one term which is differing. So somebody is calling, let's say, SVD, and somebody is writing singular value decomposition. So both of them I am treating as one term. And what I see is that other than these 2 dimensions, all the other dimensions are very similar for these 2 documents. Okay, just these 2 dimensions might have discrepancies. So let's say this has 100 and 0, and this has 0 and 100. Okay, right. So you can write this D2 document as just a very small perturbation of D1, right? So D2 you can write as D1 plus a very small perturbation of 100 and then minus 100, right? And what this will say is that, okay, my so what will happen is that my documents have some true signal and then some noise, and the role of SVD is just to suppress this lower order noise, because this signal should be very prominent. It will occur again and again in several documents, and that's why this will become very popular, or it will become very powerful, and it will become the largest singular vector, and the noise will be sort of random. So it will form the smallest singular vectors, which we will ignore. So is that clear? Hello? Okay. No response.
Okay, yeah. Okay. Yeah, I think I got it, but how does it resolve the problem of synonyms, for example? So let's say that in 2 documents which are sort of related, but they use 2 different words to.
Yeah, so that's what I sort of explained, right? That suppose I have 2 vectors which are almost similar, but they are differing in only 2 dimensions, which are 2 synonyms. So let's say, yeah. So let's say first one dimension corresponds to SVD, another corresponds to singular value decomposition. Okay, these are two of my terms, and I see that since the 2 documents have same context, so the remaining vector will be almost the same, but just these 2 documents will be drastically different. Okay, and that's why I can write this D2 as D1 plus a small noise, a small perturbation. And that's why, like, the signal is sort of formed by D1, and this perturbation will be neglected by SVD.
Okay.
Yeah. Any more questions? So let's just take a very quick example of like how this LSI works, or LSA. So let's say we have these 9 documents. Can you see the screen? Okay. So first 5 documents are related to some human computer interface system, and the last 4 are related to, let's say, graph theory. Okay, and then these underlines are the terms that we concentrate on. Okay. Using this, you can form your TF-IDF matrix. This is unnormalized matrix. Okay. So I have these 9 documents, and I'm basically these are vectors corresponding to these 9 documents. So I've represented these 9 documents in my vector space corresponding to these 9 terms, or this, sorry, 3 to 6, maybe 11 terms or 12 terms, sorry. Okay. And now what I do is I'll normalize them and compute their stuck. Okay. So what we do is we compute SVD of those 9 documents, and then project them into 2-dimensional space. So this 2-dimensional space is given by these 2 singular vectors. So this is first singular vector and second singular vector. So that forms a 2-dimensional basis, right? I project onto this 2-dimensional basis all of these 9 documents, and you can see that my 5 documents corresponding to human-computer interaction system and these 4 documents for graph theory, they are sort of separated. They are clustered far away. Okay. And that is what we wanted. That now, suppose I give you a document which is related to graph theory. What will happen is in this 2-dimensional space, it will be projected somewhere here. I will figure out one document from this side, and that's why I will be able to say that, okay, yeah, they belong to the query document that you gave me belongs to graph theory, etc. Okay. Again, my machine is stuck. So anyways, so let's let it be. I wanted to show how words are projected in this 2D space, but let it be. So okay, so one natural question is, what is the main issues with this approach? Why, let's say, Bing doesn't do this type of thing, where it uses LSA to retrieve documents for a given query, search query? So folks from IDC should definitely be able to give that answer. Why isn't it used at all, or almost, like, I don't know of any system, any ranking engine or search engine that uses LSI at all. Yeah, one is computing SVD itself is very expensive. Your term document matrix will have like maybe billion terms in real world. That's a big issue. Any other? Like another big drawback of this. Yeah, query is usually very, very small. So your documents can have, let's say, maybe 1,000 terms, and those will be well populated 1,000 terms, but the query will have barely 5 terms, and it will not be useful at all. So it is useful only for large documents or large queries. So let's say if I have a set of resumes, you give me your resume, and I want to figure out candidate whose CV is most similar to yours. In those type of problems, actually this method has been shown to work very well. Any other issue? So this method uses this bag of words model. That is, it forms just a vector space blindly. That is, it doesn't consider whether this word occurred before this word or after this word. It just considers all the words, like basically take the document, break down all the words, put it in a bag. And that is one serious problem with this approach, that this bag of word model doesn't, like, it will lose all semantic information given by the ordering of words. So for example, my head is much more important than my tail. But if I just take my HTML document, just form a, just jumble them and form a TF-IDF matrix, that information is totally lost. So, so these are like some of the issues which is why LSI is not at all used in search engine related tasks, but it is useful in this document retrieval type of tasks. And several systems are there actually that uses it. Okay. All right. So any questions, comments? Puneet, any questions at your end? Okay, so we'll meet next week on Tuesday, same time.
No, I think we are good.
Okay.
So
And
do you have any what kind of assignments will we do and things like that?
Oh, that's a good point. So actually, I wanted to give an assignment related to this thing, and now that you have asked for it, let me give the assignment then. So let me write this thing. So how do I? We don't have a course, so let me write the assignment link. So this is actually by my. I've taken it from my advisor's course. So it's almost the same sort of thing. You have these 10 documents, and the words that you have to consider are underlined. Using these words, form your TF-IDF matrix, compute SVD. I think you can use R or Octave to compute SVD, and for C#, I think there is some library called alglib or something. I search for it, alglib. So I'll just write them down. Use that library, compute SVD, and then just plot all your documents in the space spanned by first to singular vectors, and see if your documents are separated or not. Okay, so let's see how many people do that assignment. Let me write down the link. Due date will be, what should I? So due date will be, let's say 2 weeks from now. We'll tell you how to submit the assignment. Please, at least one of you. Yeah, I'll send this on mail as well. Let me write down the link as well. So we have to also figure out the registration procedure, which we haven't done so far. So www.cs.utexas.edu/users Indrajit / what is it? It's already written there. Why am I writing? 378 Spring 2009 /hw1.pdf. Okay, so we'll form a mailing list for course definitely by next Tuesday. I have to figure out how to do that. I'm hoping Vishy will do that. And next Tuesday we'll meet again at 11. Vishy will talk about exponential family. So basically we'll take off our training wheels and we'll dive right into machine learning and all the exciting stuff there. Okay. Right. Okay, Puneet. So